Okay, in this lecture, we're going to start talking about our section 2.2 material, which is on determining the volumes of solids by slicing. So to start our discussion, let's pose the following question. Let us suppose that S is some solid and that the area of the cross-section of that solid in the plane, which I'll call P sub x, perpendicular to the x-axis, and passing through x is given by A of x for all values of x from A to B. So to illustrate our problem of interest here, we have some solid shown in blue, which we're calling capital S. And let's suppose that we define a plane, which we're calling P sub x, which is perpendicular to the x-axis and is passing through a point X. So here we've got our plane P sub x, which is perpendicular to the x-axis, and it's passing through a particular value, x. And we see that when we slice our solid with that plane, we have a cross-section of our solid that looks something like this. And the area of that cross-section is what we're calling A of x. And this is true, so let's say that we're able to find the area of such a cross-section for all the values of x from A to B. So for instance, on this far end, when x is equal to A, if we take a cross-section of our solid, we have this little shape. And as x varies from A to B, we see that the cross-sections of this solid become larger and then eventually start decreasing. And then on this end of our solid, when x is equal to B, we have the area of that cross-section. So that's what we're calling capital A of A or capital A of B, or in general for any value x between A and B, the area of our cross-section is given by A of x. Now, if we have that information, let's think about how we can use that to find the volume of this entire solid. So we can consider this small cross-section of our solid as a very thin cylinder where, let me see if I can copy the general shape of this figure, where the area of the base of the cylinder is what we call A of x, and it has a very thin width, sort of the thickness of this slice that I'm taking. And the width of that cylinder, I'm going to denote as dx, or a differential of x, a very small increment in the x interval. Now, I know that to find the volume of a cylinder, I would take the area of the base, so here, the volume of that little cylindrical slice would be given by taking the area of the base of that cylinder, which is A of x, and then I multiply by the height of the cylinder. In this case, the thickness of that slice, which is dx. So this volume of a particular slice or cross-section of my solid, I'm going to refer to as a differential of the total volume, V, that I want to find for this solid. And so here it's given by A of x dx. So if we want to find the entire volume of this solid, well, I would need to add up the volumes of each of these little cross-sectional slices for all values of x ranging from A to B. So this process of adding up small slices of very thin width is the process of integration. Think about how the definite integral was introduced as the limit of a Riemann sum. So to calculate area under a curve, you were filling the region in with these very small rectangles, and then taking the areas of those rectangles, adding them up, and taking a limiting value. And that was the definition of the definite integral. So what we're doing here is the same. We're dividing our solid up into these little bitty slices that have a thin width, which we'll refer to as dx. And then we're going to calculate the volume of each slice as the area of that cross-section, which would be A of x, times the thickness of that slice, which is what we're calling dx. And in order to get the true volume of our solid, we would add up all of those slices, again, from x equals A to x equals B. So this method is known as the method of slicing. So let's make this a little more precise. We could say if S is a solid that has a cross-sectional area, A of x, in a plane perpendicular to the x-axis, at each point x within some interval from A to B, then the volume of that solid region S is given by the definite integral from A to B of that cross-sectional area function, A of x with respect to x. So in short, if we're able to determine what the cross-section or the area of a cross-section of a solid at any point within that solid, then we can find the total volume of that solid by integrating that area function with respect to x over whatever interval specifies our solid. So to make this a little more clear and see some specific examples, let's look at a problem. So in this first example, we're asked to find the volume of the solid whose base is the triangle with vertices at 0, 0, 2, 0, and 0, 2, and where cross-sections perpendicular to the x-axis are squares. So this is a typical sort of problem for this method of slicing. We're given some information about our solid. In particular, its base is shaped like a triangle whose vertices are known. So for these problems, it's often very helpful to sketch the region that's being described. And in this problem, we have the base of our solid as a triangular region whose vertices are at 0, 0, 2, 0, and 0, 2. So we would have a base of our solid that has a triangular shape. And we're told that cross-sections of our solid perpendicular to the x-axis are squares. So let's try to visualize a representative cross-section or a little slice taken out of our solid. So if I take a cross-section, we're told perpendicular to the x-axis. So if I take a little slice perpendicular to that x-axis, and let's say that the thickness of that slice is dx, or a differential of x. If I take that slice out of my solid, I'm told that it has a shape like a square. So pulling that slice out of my solid, I'm going to have a cross-section which is shaped like a square, and it has a small thickness to it, which that thickness is what we're calling dx. So I need to be able to find the area of this cross-section, which I'll call A of x. Now, for a square, we know that the area would be given by the length let me maybe call it L for right now, squared. We'd multiply length by height. If it's a square, we would have the length of one side squared. So let's think about what that length would be for a representative slice. So we can see, depending on where I take my slice, what my value of x is, I have a length that's maybe a little larger or a little smaller, depending on what value I'm choosing for x. But in any case, the length along one edge of this square is given by the length of that representative strip that I'm taking, which is the distance from the x-axis up to the line passing through 0, 2, and 2, 0. Now we know that the equation of that line would be 2 minus x. The slope of this line passing through 0, 2, and 2, 0 is -1, and the y-intercept of that line is 2. So the equation of this line is given by 2 minus x. Therefore, the height of, or the length along one edge of my representative strip is given by this equation, y equals 2 minus x. So, in other words, our length here is equal to 2 minus x. So, the area of a cross-section here, since it's a square cross-section, would be L squared, or 2 minus x squared. So now that I have the area of a cross-section taken at a particular x value, I can use this method of slicing to find the volume of that solid. The volume is found by integrating my function for area, which is 2 minus x, quantity squared, with respect to x over the x interval, which specifies my solid. So let's think about where I'm integrating from. So my base of the solid starts at this edge where x was equal to 0, and I can take slices all the way up to this right-hand edge where x was equal to 2. So I'm going to be integrating from 0 to 2 here. Now there's a couple of ways I could go about evaluating this integral. One approach would be to expand this and then integrate each term and substitute in. We could also make use of a u substitution, since our integral involves a composite function. So either approach you prefer, my own preference here would be to expand so that we have 4 minus 4x plus x squared dx. And then taking an antiderivative, we would have 4x minus 2x squared plus 1/3 x cubed. And this is being evaluated from 0 to 2. So evaluating this antiderivative at x equals 2, I would have 8 minus 2 times 2 squared would be 8, plus 1/3 of 2 cubed gives me 8/3. And then I would subtract what I get when I evaluate that antiderivative at x equals 0, which would be 0 in this case. So we can see that our 8 and -8 cancel, and so I'm left with a volume of 8/3 cubic units for the volume of this solid. All right. So let's look at another one. In this next example, we're asked for the volume of the solid whose base is the region bounded by y equals 5 minus x squared and the x-axis. where cross-sections perpendicular to the y-axis are triangles with height equal to twice the base. So let's start again by sketching our region, which is the base of our solid. So here we were told the base of our solid is the region bounded by the x-axis and the curve y equals 5 minus x squared, which is a parabola opening downward with vertex at 0, 5. So the region which forms the base of my solid would be the following region. And now what's slightly different in this example from my last example is that we're told that cross-sections perpendicular to the y-axis are triangles. So we're no longer taking slices perpendicular to the x-axis, but if I take a slice of my solid, which is perpendicular to the y-axis, let me draw a little representative slice here. And since we're slicing up our solid along the y-axis, I'm going to call the thickness of that slice dy, or the differential of y. I've got a small length along that y-axis. And I'm told that when I slice my solid in this way, I get a cross-section which is shaped like a triangle where the height is equal to twice the base. So here we're going to have a little triangle where our height is equal to twice the base. So let me maybe label my base as B, and then the height would be, well, I could call it H, and it's equal to twice the base. So this base of my solid corresponds with the base of my triangle, and then this slice has a very thin thickness, which is what we were calling the differential of y. So in order to use this method, I need to be able to find the area of this cross-section. So let's think about how to find the area of a triangle. So in general, we would have the area. And here, let's see, I shouldn't use A of X. Since I'm slicing along the Y-axis, I can see, well, the area of a slice is going to depend on the value of Y. How far above the X-axis I choose my slice. So the area of this little cross-section we're going to call A of Y instead of A of X. So the area of such a slice here is going to be A of Y. And in general, the area of a triangle is given as 1/2 base times height. But since the height is equal to twice the base, we have 1/2 base times height, which is twice the base. So our factor of 1/2 and 2 cancel, and we would have the area is given by the base squared. So let's think about how we can find this. So our base of this triangular slice is going to correspond with the base of our solid. And depending where I choose my slice, I see that I have a different value for the base. Now, one way that we can go about finding our base here is by thinking about the following. So the distance that I'm moving outward from x equals 0 to the edge of my curve, or the edge of my slice, would be x units. So of course, if I can move outward from the y-axis, left or right, by x units, then my base here, b, would be given by 2 times x. I can move x units from the y-axis outward to the right, or x units from the y-axis to the left to get to my curve. So when I'm looking at my formula for the area, I had the base, b squared, but my base is given by 2 times x. So squaring that quantity, I have a 4x squared for the area of my slice. However, what's a little bit tricky in this one is that since I'm slicing along the y-axis, I need my area as a function of y, not a function of x. So let's think about how to get that. So this distance, x, that I'm moving outward, is determined by this curve, this arc of my parabola. And this parabola that we were graphing was the parabola y equals 5 minus x squared. So if I solve that equation for x squared, I would have 5 minus y. So substituting that expression into our function for area, we had 4 times x squared, but we found x squared is given by 5 minus y. Or distributing, we would have 20 minus 4y for the area of a cross-section of my solid taken at a height of y units above the x-axis. So our method of slicing says that the volume of this solid is then found by integrating that area function, which is 20 minus 4y, with respect to y here, since we were slicing along the y-axis. And we would integrate, let's see, from where to where. So our first slice at one edge of our solid would correspond to y equals 0, or the x-axis. And we can take slices all the way up to this top edge of my solid, which would correspond to y equals 5, the vertex of that parabola. So we're going to be integrating from 0 to 5 here. So let's see what we have. Taking the antiderivative of this function, we would have 20y minus 2y squared, which we're then integrating from 0 to 5. So substituting 5 in for y, we have 20 times 5, or 100, minus 2 times 5 squared would be 50. And then we subtract the value we get by substituting in 0 for y, which is 0. So we're left with 100 minus 50, or 50 cubic units, for the volume of the solid described here. All right. So let's look at some other examples. In this next example, we are asked to find the volume of the solid whose base is the region bounded by e to the x, y equals 0, x equals 1, and x equals 3, where cross-sections perpendicular to the x-axis are semicircles. So for these slicing problems, again, we want to start by visualizing our region. That's going to help us to find a formula for the area of a cross-section. So here we're told that we're interested in the region, or the base of our solid is the region, bounded by the graph of y equals e to the x, So e to the x has a y-intercept of 1, e to the 0 is 1, and then it looks like this exponential growth function as x increases. So we're bounded by that curve, the x-axis, which is y equals 0, we've already shown, and then the vertical lines x equals 1 and x equals 3. So we're looking at the region shaded here as being the base of our solid. And we are told here that cross sections perpendicular to the x-axis, so if I take a little slice perpendicular to the x-axis at some point x, the slice through my solid would have a thin width I'm going to call dx. And if I were to pull that slice out of my solid, I'm told that it's shaped like a semicircle. So here, let's visualize what we have. We have a semicircle or a half circle, and we need to find, and let's see, it has a little thin width or thickness, this slice, which we were calling dx. And we need to be able to find the area of this slice at a point x within that interval. So in general, to find the area of a semicircle, well, we know how to find the area of a circle whose radius is known. It would be given by pi r squared. A semicircle is just half of that value. So here, let's take a look at this. We have the area of a slice is given by a of x. And in general, for a semicircle, it would be half of the area of the circle, half of pi r squared. Now let's think about how to find our radius of such a circle. So the radius would be the distance from the center of our circle to the outer edge. So when we're looking at our slice here, the radius that we want would be the distance from the center of that circle to the outer edge. And depending on where we take our slice, well, we see that radius could be larger or smaller. So if we were to take a slice on this edge at a point x of thin width dx, we see that the radius would be larger than in that first slice. So how can we find this radius? Well, it's given by half of the height of our little red slabs that we're taking, our little red slices. Now, the height of this slice taken at any point x is the distance from the x-axis up to our curve, which is defined as y equals e to the x. So the radius is then half of that value. So we would have, for our radius, 1/2 of e to the x, and then we're taking that radius squared. So let's see what we have here. Simplifying a little bit, I have a 1/2 times pi times, taking 1/2 e to the x squared, we get 1/4 e to the 2x, or grouping my constants together, I have 1/2 pi times 1/4 would be 1/8 pi, or pi over 8, and then my e to the 2x. So to get the volume, V, of my solid, the method of slicing says I'm supposed to integrate this area function, which was pi over 8 e to the 2x dx, over whatever x interval specifies my solid. And we saw here that the base of our solid went from x equals 1 up to x equals 3. So we're going to be integrating from 1 to 3. So to evaluate this integral, I might first take out a constant, pi over 8, in front of the integral. And now the antiderivative of e to the 2x would be 1/2 e to the 2x. So recall that's one of the formulas that we had derived in our section on u substitution. And then we're evaluating this from 1 to 3. So let's simplify our constant terms a bit more. I've got pi over 8 times 1/2, which would be pi over 16, times, when I evaluate at x equals 3, I would have e to the 2 times 3, or e to the 6th, minus, when I evaluate at x equals 1, I would have e squared. So this expression would give me the volume of the solid described here, whose base is this region that we sketched and where our cross sections perpendicular to the x-axis are semicircles.